This video answers the homework questions I set in my previous video called Understanding Quantum Mechanics. If you're new to my channel, you probably think it's extremely naive of me to set homework questions no one's obliged to do on YouTube videos that no one's obliged to watch. And it probably is naive, but I just don't believe that learning is a passive process. Even if you never do answer the homework questions, I hope that me asking them prompts you to think, and I hope that this video will be useful to you because it'll cover the common misconceptions from the original video, and I'll also answer the most frequently asked questions. Okay, so the first homework question was, can you do the double slit experiment with large objects and still get an interference pattern? Remember in that video I said that objects only act strangely when they're not being measured, but this doesn't happen for a big object because it's constantly being measured. So the straightforward answer to this question is just stop things from measuring it. But is that possible? People pointed out that if an object is made out of lots of particles, wouldn't the different particles interact with each other? And what about gravity? Every object is interacting with other objects via gravity, and so doesn't that mean that nothing can escape being measured? There were lots of great questions along these lines, and somehow they all boil down to this bigger question. What is a measurement? This is easily the million-dollar question in quantum mechanics, and it's still unsolved. And so we're going to talk about it in lots and lots of detail in the main series. But for now, I want to address a misconception that I can debunk that I saw in the comments a lot. People thought that when I said measurement, what I really meant was interaction. In other words, they thought that if a particle interacts with another object, it has necessarily measured it. And I can see why you would think this, since all my examples of measurements were about particles hitting other particles. But this is not necessarily the case. Actually, a measurement is when you get information about what the particle is doing leaking out. Let me explain. In one example that I showed, the object is hit with an air molecule. But the point is, the air molecule will change its own path depending on where the object is. If it's here, it'll bounce off like this. But if it's here, then the air bounces off like this. And so, since us seeing the final state of the air molecule is enough to decide where the object is, we say that the air molecule is carrying away information about the object's position. And that's what makes this a measurement. Not the fact that the air is interacting with the object, but that it's leaking information about the object to the outside world. Let me explain this point a little bit further with another example. Suppose that you have some weird hypothetical thing that changes color when it comes into contact with our object, but it goes straight through it. This is clearly some sort of weird interaction. Now, say the object can be either here or here again, and the thing comes in like this. In either case, the final state of the thing is this. The thing clearly interacted with the object, but it hasn't measured it, since it gives you no information about where the object is. That's an important point, so I hope it's a bit clearer now. Now let me get back to the question about when our object is made of different interacting parts. For simplicity, imagine our object is just made out of two bits stuck together. If one of the bits is in this position, then you know that the other bit has to be here too. And similarly, if you know one part is over here, then the other bit would be there too. And so clearly this one bit does contain information about the other. The reason this doesn't count as a measurement, though, is that this information isn't being leaked out to the wider world. And so for it to count as a measurement in quantum mechanics, it's really important that the information be carried away, and you can no longer interact the two particles together. There's a reason for this, and it's something I'll cover in detail in the main series, but for now let me convince you by appealing to experiment. The double slit experiment has been done with many things made up of composite parts. Many of you mentioned they've done it with buckyballs, which are molecules with 60 carbon atoms, and still saw the interference pattern. But apparently it's been done with molecules with over 800 atoms as well, and it still works. So composite systems can have interference. Another great question I got a lot was, what about gravity? Does that count as a measurement? To answer this, I'd need to assume just slightly more quantum mechanics than I've taught you, so I'm going to set this as a homework question in the third main video of this series, and you guys can give it a go for yourselves then. And I'll give you my solution in another one of these videos. But getting back to the actual homework questions now, the second question was, imagine if you had some measuring device that could actually measure which door an electron went through. What would happen? Remember, I'd said that electrons act strangely when they're not being measured, but right now it is being measured, and so it has to act normal again. For an electron, that means that it has to be in just one place. You won't see it go through both slits, just the one. But doesn't this contradict what I'd said previously, since now we know each electron is going through just one door? No, because now the pattern on the wall is no longer the interference pattern. Instead, it's exactly what you'd expect in the case each electron goes through one door, which is what's happening in this case. Quantum mechanics is sneaky. Question 3. This one's about Bohmian mechanics, and I'll keep it short because I've talked myself hoarse about this theory before. The question said, in Bohmian mechanics, aka pilot wave theory, the electron does in fact go through just one door in the double slit experiment. But in my last video, I seemed to rule out that possibility. So what incorrect assumption did I make? When we looked at the single slit experiment, we saw electrons go vaguely here. So we assumed that if electrons were really going through one door each, an electron going through door 1 wouldn't mind whether the other door happens to be open, and it would just do what it was going to do anyway and end up vaguely here in any case. That's how we got a contradiction. But that's not the case in Bohmian mechanics though. The electron does go through this one door, but it cares a lot about whether the other door is open. That's because it has this thing called a guiding wave that spreads through all of space and tells the electron which way to go. So when both doors are open, the wave goes through both doors and then tells the electron to go somewhere else. Okay, so those were the main homework questions. Let's have a lightning round of responses to other common comments. People asked, doesn't the single slit pattern actually look like this, with one main band and a few fainter bands on either side, whereas I always draw it as this? The answer is yes, I just draw the main chunk because it's easier and clearer, but I could have done it properly and nothing would have changed in any of my arguments. Next, there were lots of people who tried to answer homework question 1 by using this equation called the Broglie wavelength. I made a video about the uses and abuses of that equation, but basically that equation is only valid in very, very specific circumstances, and one that almost certainly doesn't apply to a complicated real-world object. Also, I got a lot of comments saying that I was wrong about waves because of quantum field theory, or that I should talk about quantum field theory instead because all the paradoxes clear up when you look at it. Actually, I think the paradoxes of quantum mechanics just get compounded in QFT, but that's something to talk about much, much later. And that's all for this video. Thank you so much to everyone who did leave a comment on my last video, and I really encourage all of you to give the homework questions a go in the future. But unfortunately, while I love reading and replying to all the comments, soon it'll be too much for me to reply to each one personally. I'll keep reading them all, and I'll reply to as many as I can in the future, but that's where I'd love for all of you to help me and comment on each other's work. As I saw in the comments last time, that leads to way more interesting discussions anyway. I try to ask questions that can be answered in multiple ways so you guys can learn from each other. And this works when we all treat each other with respect and remember that we're all here to learn. Thanks, guys. See you for the second proper video in this series.